how to implement this multi-level inverter in the Simulink platform. Maybe some of the participants, they might have already done some of the work in the field of multi-level inverters, and also have done some, might have done some simulation work. But I'll be doing some of the hands-on with Arduino controller, how to implement in experimentally. So that part I will discuss in the next session. So before that, let me just discuss today with related to the theoretical aspects of multi-level and also the switched capacitor types. So here, as we all know, what is this multi-level inverter? This is nothing but a advancement, or you can say 5 level, 7 level, like that. So a high power inverter, you can say, which generally generally used applications nowadays in the STATCOM application, photovoltaic application, high frequency applications, as well as the drives applications. It has been used since like last 2 decades mostly. So why it is used? And because as you know, when we increase the number of levels in the output, a 3-level inverter, if we consider, the output of a 3-level inverter is generally a like it is a square wave, and it consists of one positive half cycle, one negative half cycle, and a 0 level. So that is called as a 3-level output. When we connect directly this kind of inverter in the grid, or if the load side, if we consider grid is connected, so in that case the harmonics will be very high. And also, if we cannot directly connect to the grid, it's because we need filters in the interfacing filters, we can say. So the size of the filters will also be very large. So if we just replace the 3-level inverter, 3-level or 2-level inverter with multi-level inverters, the power quality can be improved with respect to the voltage quality, we can say, because it is creating multiple steps at the output. So that will reduce the harmonics, one thing. Second thing, as it is reducing the harmonics, the size of the filter at the grid side, that can be reduced. So that is one of the important advantage of the multi-level inverter. And but what is the problem with this is that it contains a number of switches and DC sources generally. So because of this number of switch and DC sources, the problem is the size and cost will be very high in real time. So in terms of industrial application or the applications whatever I have just specified, in terms of that, we need to focus on reducing the size of it, and there the switched capacitor comes into picture. And I'll introduce how the switched capacitor inverters have been evolved. So before that, let us see some of the conventional inverters. Conventional inverters in the starting, what from the last 2-3 decades, what has been started. So this is the 3-level structures what I have shown here. The neutral point clamp type, you can see, and one is the flying capacitor type. Another one is the H-bridge type. So these are all 3 levels. So this is all this DC sources, what is there in the input, that can be replaced with the renewable energy sources, as I have shown on the top. You can see this DC sources, this point clamp type, flying capacitor type, cascade H-bridge type, all these types has been successfully integrated with photovoltaic systems, and many research work has been done in this area. So you can see this all 3. Basically, the first 2 types, the neutral point clamp type and your flying capacitor type, if you see, these 2 types generally contains a single DC source, and there are number of diodes and capacitors. So when you increase the number of levels, because these are, as I said, these are 3-level structures. So when you increase the number of levels, with that, obviously the number of diodes and capacitor is going to increase. And one more problem is that when capacitor comes into picture, you need to have voltage balancing of these capacitors. And when diodes and like point clamp type, when you are increasing the number of levels, the modules are connected in series. So there is a high chance of failure here. Failure rate is high. So with these problems, the cascade H-bridge type, that again got evolvement. And you can see the cascade H-bridge type, as the name suggests, we can just go on cascading the number of H-bridge modules, so as to increase the number of levels at the output. So that is more scalable and highly modular, because we can extend it to high number of levels without addition of any capacitor, additional diodes and capacitor. Whereas if you see this 3-level inverter, As you can see, this is a single phase structure and which requires four switches like T1, T2, T3, T4. Four switches are there. So when you go on increasing the number of level, obviously the number of switches is also going to increase. So this requires large number of switches, and there the problem comes when the number of switches increases. So this all these three inverters, as you can see on the right hand side of the screen, they are used in the industrial applications also, like Siemens, ASI, Rubicon, Alstom, Rockwell. So like this, they have installed this neutral point clamp type inverters, cascade H bridge type inverter, flying capacitor inverters. So all these conventional inverters have been used in the industrial applications also. So what I can do, I can divide this all these multi-level inverters what I am discussing, because I told you, we are going to concentrate more on reduced switch types, how the switch reduction and cost reduction has got evolved. So this reduced switch, all the multi-level inverters, I divided them into two different types. One is the single source type, another one is the multi-source type. As in the previous slide I have highlighted, these two types, neutral point clamp, flying capacitor, these two are basically the single source types. Whereas the cascade H bridge, if you go on cascading this same module with another one, obviously the number of DC source is going to increase. This number of DC source is going to increase. So that is why that is called as multiple DC source type. So it needs multiple isolated DC sources. So with this multiple isolated DC sources, there also comes another advantage. You can operate this inverter symmetrically. Also, you can operate this inverter asymmetrically. Means you can take the sources equal, so that is called as symmetrical. If you take the sources asymmetrical, or the sources are not equal, let's suppose the sources are in the ratio 1:2 or 1:3, like that, that is called as asymmetrical structure. And there are also some of the hybrid structures. So we'll see here some of the structures. See here, these are all the reduced switch type, symmetrical and asymmetrical structures what I have shown here. So these three structure what I have shown here, these are all symmetrical. If you operate with the sources, or if you take the sources all equal, just a second. So if you take all the sources equal, that is called as symmetrical type. So here you see this structure. In the first structure, if you see, there is a DC source and there are two switches. So this DC source with two switches, that is used for generating the levels or creating the levels, you can say. And whereas there is a bridge or full bridge, you can say T1, T2, T3, T4, like that, there are four switches are there. So that is four switches will help in creating the polarity, or help in changing the polarity. You can say positive and negative polarity can be obtained with this H bridge circuit. Whereas your this side or left hand side, you can say the DC source and two switches. So that is actually helping to produce number of levels at the output. So we'll also see in more detail, no doubt. This is just a structure review of some of the structure I am showing you, so that we will have idea how this reduction in switch is done. So here, all these three structure you can see that are why these are called as reduced switch. First thing. So here, if you see this H bridge in the load side, that is no doubt generating the or reversing the polarity, just positive half cycle and negative half cycle, that is being created. Whereas this in the input side, you have only two switches. But now if you just compare it with a conventional structure, you need to go on cascading four switches every time, right? So here we are not cascading the four switches. Instead, we are just cascading the input side, you can say. So input side with two switches, we are just cascading. And similarly, other structures are designed. And what is the disadvantage of this structure when there is a bridge like this at the load side? I'll just highlight one important point here. You see, here, if you focus on any of these structures can be operated symmetrical also asymmetrical. Asymmetrical means if you take the ratio of the sources, let's suppose this is V, and another source if you take as 2V. So like that, if you take different sources with different voltages, that is asymmetrical structure. So what is the disadvantage of this H bridge in the load side? So that disadvantage is that these four switches, T1, T2, and T3, T4, these four switches has to block highest blocking voltage or highest stress. This has to withstand the high stress, right? So this high stress, due to high stress, These four switches has to be of highly rated, and obviously that will incur more cost also when you are trying to implement this type of structures. So you have to, that is an important point, that when you try to reduce the number of switches, with that you have to also focus on how much stress across each of the switches an inverter is facing. Because in practical design, when you want to implement in industrial application or photovoltaic systems, stress is a very important aspect. So you need to think about how much stress each switch is facing. Stress and standing voltage are almost equal. And what is the standing voltage is actually in terms of definition, if you see, when this switch is not operating, any of the switch, let's suppose T1, T2, any of the switch, when these are not operating, at that time, how much stress across this switch? So that is called as the standing voltage. So that you need to think of, because when it is off, at that time, it may face very large amount of voltage. So that I will also means detailed analysis. Will do it with one of the structure. We'll take one of the structure and we can just think of how the stress analysis can be done. Okay. So these are some of the structure. As I have told you, stress is the main important point. So just focusing on the stress, researcher have proposed some of the other structures here, as you can see. These all the structure, they do not contain an H bridge, right? So there are four switches like H bridge that is not required at all here. You can see. So these structures are basically that I have named as hybrid or modified type topologies. And if you want to know more information regarding this all these structures, you can refer to one of our paper. This is one of the well-reviewed paper, you can say, and you can go through this paper to find out all the different types of reduced switch multi-level inverter topologies. And also we have taken two different aspects: renewable energy integration and drives application. So with these two different applications perspective, we have done a review on this different type of topologies. Also, you can see the comparison with respect to number of switch, number of diodes, capacitors, everything in detail. The comprehensive analysis has been done here. So you can just refer to this of the one of our work to know more about this all these structures. So here, taking into account this number of switches, we have designed one structure in our laboratory. So this structure, as you can see, that requires multiple PV panels, right? And all these multiple PV panels, you can see they are taken in different ratio, that is 1:1, 2:2, because this DC-link voltages here are maintained in asymmetrical. So this structure, I can say it is operating in asymmetrically, and it requires multiple PV panels. And this has been connected to grid, and it has been tested with in grid connected mode. So when you want to test in grid connected mode, obviously you need to also focus on what is the maximum power tracking from the PV side, input side. From the grid side, if you see, you need to operate the inverter, everything, and you need to operate always in unity power factor, right? And one more important point is individual, because there are multiple number of PV panels are there. So individual DC-link voltage control is also required, right? And also you need to maintain the power quality when you are integrating with the grid. So taking into account all this, and one more thing I want to highlight here, that this inverter, what structure, what I've shown here. So because of these asymmetrical sources, we are able to generate a 15 level output like the one which is shown in the right hand side of your screen. So we can generate a 15 level output, as you can see here. So this 15 level output, how to produce that is by PWM switching of the switches. Whatever number of switches connected here, as you can see, there are around 10 number of switches connected for generating a 15 level output, right? Also, there is another advantage that we can extend. This structure can be extended to any number of level if you want to. This can be extended. So, so this structure produces actually 15 level output. So as I've said, to produce 15 level output, you need to have PWM switching scheme of all these switches. So that also we'll see in the that what is that called hands-on training session. I'll also highlight how this PWM switching scheme can be implemented, because that is the main basics of this experimental investigation. If you want to do in real time, you need to focus on how the switching pulses can be generated, right? So that I will be discussing of different modulation control techniques used for multi-level inverter, and also how it can be implemented in real time. That I will discuss in the hands-on session. So let us move ahead with this. If you want to implement here for a photovoltaic system, this kind of system where there are multiple number of PV panels are there. As I've told you, if there are multiple PV panels, first thing you need to focus is the maximum power tracking from all the PV panels. So for that, we have implemented here, if you in the input side, you can see in the control structure, there are multiple MPPT controllers, right? And this is all we have considered here incremental conductance algorithm for tracking the maximum power from each PV panel. And all this fully integrated controller has been, this control structure has been done in the DSP environment. And you can see here, I have highlighted different points. What the first thing is, we need to control the individual DC link voltage, right? So for controlling each PV panel DC link voltage across it, we have connected here, as you can see, individual DC link voltage controller modules, right? And also, after that, we have connected one of the total voltage controller module here. Why this has been connected? Because only maintaining the individual voltage across each DC link is not valid, because you cannot just operate in control loop, or you cannot operate a system like that if you maintain individual DC link, because total DC link voltage has to be also maintained for feeding the constant power to the grid, or continuous power to the grid, you can say. So in this kind of system here, one important thing, like another thing we have taken here, the current controller module. Why this current controller module is taken? Because that is again maintaining the power, the power balance thing, you can say. So we are maintaining the power balance here by integrating a current controller module again after this, after the voltage control module, right? And if you see another thing, all this individual DC link voltage control module is giving a signal through this PLL. PLL is used for synchronization with the grid, and that is used for generating the reference signal. Here you can see this reference signal is going to be used for developing the PWM control scheme for the structure, right? So here in the below box, you can see I have highlighted here, phase disposition PWM control scheme is here used. And this PWM structure, this PWM control, it might looks complex to you for a 15 level inverter, but it is really very easily you can implement if you once understand how to implement the logic in real time. So here, this is the PWM control scheme. The logics also, how the switch is getting pulse, that logic we have also written here, if you see. So for each and every switch, we have mentioned the logic here. So that is how it has been controlled. And if you see the experimental setup here, you can see, and also there are some of the experimental results I have highlighted here with respect to varying the modulation index. You know, right? Modulation index, if you keep very low, obviously there are two different things. One is you cannot get the full output voltage what you need. Another one, it will also increase the harmonics in the system. If you operate at low modulation index of 0.5 in real time, if you see, this is the inverter output voltage. Here the inverter is generating around 1, 2, 3, 4 steps in the positive. So it is 9 level output is generating in the output. But whereas our inverter has been designed for getting the 15 level output, right? So as we are getting 9 level output, that is due to the lower modulation index. And also you can see the grid current, what is shown in the green color, that is also very less, right? So continuous power, you cannot feed it to the grid here in this case, and also harmonics will be more. So in the second case, what you have tested here, maintaining the modulation index nearly more than 1. If you take it more than 1, you can see here the upper level in the output voltage is more flattered, right? So as the upper level is flattered, that will also incur more harmonics. And also the grid current also, if you just see clearly, on the top of the grid current is somewhat flattered. So obviously it is not clean sinusoidal waveform, and harmonics will be more. So that is why we are maintaining always the modulation index nearly 1, as I have seen in the third case here, nearly 1. And you can see at nearly 1 modulation index, clearly we are getting a 15 level output, right? So 15 level, why I'm saying this, some of you might have got some doubt with the levels, how I'm counting. Levels is not 7 in the positive half cycle, and 7, this is the ground level here. So there are 7 steps in the positive half cycle, 7 steps in the negative half cycle, and there is a 0 level. right? So there are 15 levels when I say. This is how we can count the levels here. So I'm getting the 15 level output. So here I want to highlight one important point. As you can see, this output is staircase type, and also it is nearly not sinusoidal, but it is approaching to sinusoidal if you increase the number of levels, right? So for a 3 level inverter, if you see, that is generally like this, a step to waveform, like this, a step to waveform for a 3 level inverter. But whereas when you see this your multi-level type, that is generally containing a number of steps in the input. So because of the number of steps, the harmonics is getting reduced because it is approaching the sinusoidal type waveform, right? So in the voltage itself, we have reduced the harmonics. So obviously current harmonics will be definitely reduced, and we are maintaining clean sinusoidal, as you can see the grid current here. And I have also presented here with power quality analyzer. You can see that the inverter voltage TSD is very, very less for a 15 level output, and grid current TSD is also 1.7% nearly. So that is IEEE 5.9 standard is following this grid connected inverter. And some of the other tests which is taken, because it is connected to photovoltaic system, I have said. So with respect to change in photovoltaic panel, your inputs like the irradiation, we have tested one thing. Second test is conducted with respect to the sudden drop in grid side voltage. Other key results with respect to different dynamic test conditions, you can refer to this paper what I have highlighted in the previous slide, right? So in this paper we have highlighted all these different types of dynamic test conditions. So here, if you see, this is the result from a solar simulator, right? You can see that in the solar simulator we have set the power to around 93.5 watt, right? According to the voltage current I am telling. So with 93.5 watt, this is the measured when you are connecting, right? And what we are calculating when the load and grid is connected, you see it is tracking or extracting almost the maximum power is tracked here, right? Whatever is calculated, sorry, this calculated power here is 93.5 watt, and what is measured, it is 93.55 watt. So you see we are tracking almost 99.5% in the MPPT, right? In the second case, when the irradiation changes to around 600 watt per meter square, because of change in irradiation power, the maximum power has been changed, reduced, you can say. So here also 48.64 watt is the calculated power, and we are measuring 48.61. So obviously 99.5%, more than 99.5% tracking efficiency of this tracking, you can say. So these tracking curves have been obtained from the simulators, and you can see here with respect to change in insolation, suddenly the grid current, the 15 level output is maintained, right? There is no distortion in the grid voltage in the second case. In the third thing, that is the grid current, you can see that is decreasing because of the reduction in the insolation, right? Or you can say irradiation. And so that is how the like inverter is operating satisfactorily to obtain 15 level output. Another case, you can see grid voltage sag condition. So here you can verify the controller action. Because of sag, what is happening here, you can see the grid voltage. I have also, that is why highlighted with marking how, because you can clearly see how it has been changing. The voltage is reducing, you can say, right? So when there is a drop in grid voltage, the red color graph, you can see there is a slight increase in the grid current, the green color one, right? So why this is happening? Because this I have highlighted in the controller action, the current controller module, why you have connected to balance the power, right? So whenever there is a sudden decrease in the grid voltage, to balance the power, grid current is increasing. So the controller is also running very smoothly, you can say. With a sudden decrease in grid voltage, it is also working properly to maintain the power balance. So with this, till now, whatever I have shown you, that is related to all multiple PV panels and how multi-level output is obtained. But as I have told you, this all requires multiple PV panels like this, you can see. And you can also integrate DC-DC converter. Why DC-DC converter is there? Obviously, we need to boost the voltage to some extent, because because photovoltaic panels in real time, it is available in low voltage rating. If you want a boost converter, you can integrate. But you can also think of going to single stage, because there are multiple number of PV panels are there. So you can avoid the DC-DC converter to make a single stage system. But what I want to highlight here is that in these systems, whatever I've shown the multi-level inverter system, you need multiple PV panels, right? That is the one of the point to focus. And in the traditional system like 2-level or 3-level systems, if you see, there we also need boost converters are required. Every photovoltaic system, wherever it is integrated to the 3-level inverters, they're generally connected DC-DC converter, boost converter. And now the inverter in the market, what is available, that is all integrated types. Inbuilt boost converters are there. So you can just boost the voltage. Also, you can convert to AC. Whereas you can see the output. This output, whatever I've shown, that is a 3-level output. That is square wave type, right? But in the multi-level output, what you are getting is the multiple steps at the output. So multiple steps you are getting, but you require multiple PV panels. Here we are getting the harmonics is very high. That is a problem in the traditional system. So to avoid all this or to overcome all these problems, what I have suggested here in the right hand side of the screen, you can see what is being suggested: to use a photovoltaic panel and avoid DC-DC converter. So boosting is not required. If you do not do boosting here, or boost stage is avoided, so what you can do, you can design an inverter such that you will achieve boosting also with that inverter. So this inverter, whatever I've shown in the right hand side, that is also producing a multi-level output, right? And with the integration of switched capacitor, we are able to boost the voltage. So we are avoiding the DC-DC converter. So that is one of the advantage of this switched capacitor type inverters. So before going into introduction of switched capacitor type, if anyone is having any doubt, you can just tell me here. You can unmute and ask me if anyone is having any doubt till this. Or else I'll proceed.
Hello.
Yes, yes, please.
Hello. Hello, Mr.
Yeah,
Panda.
yeah,
Am I
you're
audible?
audible. Please tell me.
Hello. Yeah, Mr. Panda. Actually, I didn't get the power balance in your algorithm. I didn't get that.
No, power balance. There is no such algorithm for power balance in the
Because
in the control structure. What you have done?
you have given a statement that you are balancing the power in a single phase. By looking at the circuit diagram and the experimental setup, I understood that you have done the experiment for single phase.
Yes.
If that is the case, then what is this power balance in this single phase? Is it with respect to certain individual module, or with respect to any number of phases?
No. In this, with just a second.
Can I see the slide? Like
Yeah.
control algorithm?
Just a second, because this slide has got closed because of some reason, I don't know. I'm just opening it again.
Okay. Meanwhile, I have another question.
Yeah.
May I know what is the power level that you are proposing this particular converter?
Yeah. We have also tested for around 1 kilowatt, and up to 1 kilowatt we have tested these inverters, because that power level I thought
Fine,
of.
Panda.
Yeah, the power level
Fine,
case I
Panda.
thought of
The thing is
introducing after the switched capacitor type, because when you develop switched capacitor type inverters and all, this power level has to be put more focus, right?
Hello.
Yes. Am I audible?
Now it is clear. I didn't get your voice was breaking.
Okay. So what I'm telling is, when we
I
design switched capacitor type inverters, then at that time this power level is the more concern. But here up to this point, power level I've not discussed. I'll be discussing in switched capacitor type how this power level and all this plays a major role. Yeah, to answer your question, what you're asking, how to balance the power and all, you see, we have integrated here voltage control module and also a current control module, right? The
okay. It's
grid.
an outer loop control. The first
Yeah,
one
yeah,
is.
correct.
The second one is inner current control.
Yeah.
Yes.
So with this,
What
we are
about the
maintaining.
individual voltage control and why it has been added to the first reference generation current?
No, individual voltage controller module, that is doing the DC link voltage control, right? With
Yes.
that DC link voltage controller, what we are doing, we are taking the reference signal for generating the reference current for PWM generation, because it has to run in a closed loop environment kind of thing. So what we can do here, if you see here, I'll just make it full screen. So here, as you can see, this individual voltage control modules output that are all giving a voltage signal, and that is taken as reference voltage. That reference voltage is taken for, because see what is the problem here in this type of modules. If there are number of PV panels are there, they might operate differently, because this might be one module might be operating at 1000 watt per meter square, another module might be operating at 750 watt per meter square. So that requires a distributed MPPT kind of thing, right? So because of this distributed MPPT control, you need to have both the individual voltage controller, also total voltage controller. Both the things you need to integrate, because otherwise in other case, what you cannot do is you cannot maintain the required voltage here. So the thing is, you see here, one more point I'll highlight here. 1x1 module, why I have taken, because let's suppose this initial first voltage is V, okay, and the second voltage, you can see this is another separate voltage, right? That's different. So if they are different, and if your modules are also operating differently with respect to different irradiation, what will happen in that case? If you are not maintaining the desired voltage across this DC link, each individual DC link, these steps in the right hand side, I have shown the output voltage, right? 15 level output voltage, you can say. So what will happen? These steps are not equal now in that case. If you are not maintaining the DC link voltage across each PV panel, see, I have maintained the steps here 0.5 B, then 1 B, then 1.5. So each step is here 0.5 voltage. Are you getting? Yeah. So each step here is the 0.5 volt. So if you are not maintaining the voltage as desired, the what will happen? One step may be 0.3, another step may be 0.7. So we have also faced the problem in the real-time applications. If you are not maintaining this voltage as required, the steps you will see they are unequal. And if the steps are unequal, definitely it will introduce a large number of a large amount of harmonics in the output. So you need to also focus your output should be very much symmetrical in the positive and negative, and also steps, right? Yeah. So these are the points, and yes,
whether
please.
the regularization of voltages will limit the MPPT?
No.
Since you are trying to regulate the here I can see that individual MPPTs are being regulated by using an MPPT controller.
Yes.
And then it is being processed to an outer voltage controller, which are supposed to be regulated.
Yes.
Right? Here, individual voltage control module is there.
Yeah.
After that, the control signal that is processed out from this individual voltage control,
yes,
right? It is being fed to the current. You see, that is being fed to the current first point.
So here, yes,
in the upper one, I reference.
Yes.
Yes. It has been processed to I reference.
Yes.
Right? And the same information is processed to the V reference.
Yeah.
Should I think that it's a current reference, or should I think that it's a voltage?
No. This is no doubt this is a current reference only. Here, what is generated, right? Current reference only, but it has been.
If that is a current reference, then how it is going to process to voltage?
Yeah. Then you need to actually that is what I told you, because I am not taking all the equations in the closed loop. How it is being generated the voltage reference after this current reference. If you want to know that, you need to focus on this paper. There we have mentioned.
Mr. Panda, your voice is not clear.
Hello. Am I audible now?
Panda, your voice is not clear.
Just
yes, I can speak now. Mr. Anil Kumar, I think, putting the questions, I think. Yes. Am I audible, Mr. Anil Kumar?
Yes, sir.
Yeah.
Yes, sir, yes, sir.
What are the difficulties? Your point-to-point question you are putting, that is fine. But the detailed analysis is available in that paper, right, which paper is already published. There you can see that I reference, how it becomes the V reference. Okay, that is your question, hopefully. But the detailed equation, unless until it is given to you, you cannot understand. That is only available in the published paper. Yeah, Kaibalya?
Yeah, sir, am I
You
audible,
want
sir?
to say that thing or what?
Yes, yes, yes.
What is his question?
Yes, sir.
Hopefully, his question is that you are feeding the one is a V reference, another is I reference. How it is
Yes, yes,
a
yes.
comparator?
Yes, yes. He has correctly pointed out, but for that, I suggest him to follow the paper so that you can follow all the equations related to the control scheme and how it has been generated, stability analysis. Everything has been done in the paper. I suggest to follow the paper. Here, I have not presented
Okay,
the equations and all these things, right? And yeah, any more questions?
okay, fine.
Yeah, you can communicate to us.
Right now, no, I think
If you have any other doubts, also you can communicate through email. Definitely, we will help you out. Uh,
yeah, thank,
but the minute
okay,
analysis cannot be presented here. Okay, we can go for other participants if
okay.
they have any question.
Thank you, sir.
Otherwise, Kaibalya can continue.
Yeah,
Yes, please. Thank you, sir.
yeah, Anil, Dr. Anil Kumar Bonala, can I know your background?
No, no, maybe he is doing
I
the
have
research
completed my
in that
PhD from
area.
NIT Warangal.
Okay,
Yes,
okay,
sir.
okay,
I have completed my PhD from NIT Warangal. Right now, I'm
okay,
working in Vagdevi Groups.
okay, okay,
My
sir.
area is completely on multi-level inverters connected to grid.
Okay, okay,
Okay.
glad to know that. That's why I asked you whether you are working
Uh,
on this same field or not.
Yes, yes. That's why he is putting
I'm into the
in
same field
and
and
taking the interest. Okay. Yeah, it is a
Yeah,
good
yeah.
thing, and we will be in touch with you definitely, and let us
Yes.
know
okay.
afterwards. Okay.
Good
Because
evening, sir.
many participants
Okay,
are here,
fine.
and
Good evening, sir. Good evening, sir.
yes,
Myself, Subhasis. I have
yes, yes.
posted a question in chat box. Can you see, sir? Chat box, I
Uh,
have given a question. Sir.
yeah, yeah, we'll see. Let him to complete the presentation, huh?
Okay,
Because
sir. Okay, sir.
he will be with you for 2 3 sessions. No problem.
Thank you, sir. Thank you, sir. Thank you,
Yeah.
sir.
Here
Okay, sir.
we'll take your
Okay, sir.
queries.
Okay, sir.
Okay.
Yeah,
Thank you.
yeah. So I will see the chat box and do the all the questionnaire. I will take it. So before that, I will just introduce here the switch capacitor module, and then I'll stop. And here one important thing what till now I have highlighted, as you can see, the upper part is the 3-level circuit, and it is giving a 3-level output. And you can see the lower circuit. That is how we have cascaded to generate a more number of steps in the output, right? We can generate more number of levels in the output, you can see. So 5 level it is producing, and in the 5-level circuit, when I'm taking all those input voltages equal, right, V and V, so here I'm generating 2 steps and the output is 2V. And you can see that there are 8 number of switches, right? 4 switches in the top module, and there are another 4 switches in the bottom module. So there are 2 modules cascaded to get this output. So likewise we can go on cascading, no doubt. But what is happening here, the number of switches is multiplied with 4, you can say, or 4 number of switches are every time getting added. So that is how it is going to increase the number of switch. So because of that, what is proposed in the right hand side, you can see in the screen what I have done it here. Here in the previous circuit or cascade HVS module in the 5 level, what we are doing exactly, we are just going to add the voltage sources by cascading it, right? So instead of adding like this, what we are doing here in the right hand side, you can see I have just connected one switch. Let me turn on this pointer. Yes. So here you can see S2 switch, what I have highlighted. Why that is used here? No, the S2 switch is now getting used here to add the voltage sources V1 and V2, right? When I turn this switch on, what will happen? Because the current will flow through V2 and V1 both. And obviously this T1, T2 are used for, as I've said already, I have highlighted T1, T2, you can generate the positive half cycle output. T3, T4, you can generate the negative half cycle output. So now let us consider T1, T2 are operating. What will happen if S2 is on, right? If S2 is on, the both the voltage sources is going to add. So that is how we can generate the steps. And if in the first level, what I do, I'll switch on S1 in the first level, right? So that will create the first voltage steps because of the source voltage V1. Only V1 will operate through T1, T2. So current will flow in this path. So what will happen? Only V1 is appearing across the output. So let's suppose first step is produced. Then in the second step, if you want to produce, you can just switch on the S2 switch. Now you can ask me why I've connected this S3 switch then. Obviously, there is no need of this S3 switch. But what I have highlighted here, if you now take both the voltage sources asymmetrical, in that case, what will happen? Just think of. In that case, if the load is inductive, because you have to think, if you are designing an inverter like this, you have to also think for different loading systems, right? Resistive load, inductive load, nonlinear load, everything you have to consider. So considering inductive loads, if you consider here, if these sources are asymmetrical, in that time, to flow the negative current because of the inductor, some of the negative current will flow back to the supply, right? So because of that, there is a path to provide path, S3 switch is required here. But otherwise, if you take the sources symmetrical, definitely S3 switch is not required. So why I've shown this circuit here on the right hand side, how this switched capacitor now is coming into picture, you can see. Now I have added another circuit here. You can see here the same circuit. What I have replaced here, one of the source V1 that I have replaced with a capacitor, right? And another source is there. So you can see what is the interesting feature of this circuit now. There is only single source, first point. Second is, now when it is operating, how it will operate now? Very simple. It will, when there is no switches are on from this level generation module, what I have highlighted in the red color box, there are two switches, S1, S2, two switches are there, T1, T2, T3, T4, four switches that are used for polarity changing. Now you think of, there is no switches, like S2 is not on, right? And if only diode is conducting, so how the current will flow first? So the current will flow through the diode through T1 and T2, right? So when current is flowing in this path from T1 and T2, what will happen? We'll just turn on S1 also. So if you turn on S1 also, some current will also flow through this capacitor, right? So when the current is flowing through the capacitor, this capacitor is going to get charged. Clear? So when this capacitor is getting charged to the voltage, the same voltage of the input voltage in the first level itself, right? First level, how it is produced? V is getting, the supply voltage is getting connected to the load through T1 and T2. So obviously first level is produced and the capacitor is getting charged because S1 is on. Now in the second level, in the second step, what I can do after some time, S1 I can turn off, I can turn on S2. So now you think, if you turn on S2, what will happen? The voltage V and capacitor C both are getting now added, because capacitor has initially stored the charge to V. Now it is getting discharged because of turn on of switch S2, right? So when a switch S2 is turned on, through the capacitor current will flow and T1 through T1, T2. So what will happen? The voltage now, the output voltage at that time will be V plus capacitor voltage, that is V again, is 2V. So we are generating two steps at the output, that is clear. And also with using single switch. Now see the interesting feature, there is a single DC source, right? And you are getting two steps at the output, and what is the maximum voltage is 2V. The same output what I have shown in the left hand side, that is the same output this circuit will also produce. Now how many number of switches are there? Only 6 switch. So we have reduced, with respect to conventional circuit, if you compare, we have reduced 6 switches, to reduce to 6 switches. The conventional circuit require 8 switches for 5 level. This requires 6 switches. Here there are multiple sources are there, right? And here there is only one single source. Here this circuit, in the conventional circuit, it cannot boost the voltage, because whatever supply voltage we have, same output we are getting here. V is there, so we are getting 2V. But here with V in one single DC source, we are getting the voltage 2V. So we are able to boost it to 2 times. Now you can think of, if you want to avoid a DC-DC converter, right, with respect to photovoltaic system application, you can avoid a DC-DC converter, because this circuit, because in DC-DC converter, what we are doing generally, we are maintaining the 0.5 duty ratio to boost it to 2 times, I am telling. If you want to boost the voltage to 2 times, we have to operate at 0.5 duty ratio nearly, right? So that 0.5 duty ratio and DC-DC converter, all these things can be avoided if you are doing a circuit like this. Only thing here is that you have to focus is the capacitor size and all. Capacitor size, no doubt, for a lower power level circuit, capacitor size will be lesser. And you have to maintain the capacitor voltage. Whenever a capacitor comes into picture in a circuit, most important thing is that how you will balance the voltage across the capacitor. Now again, if I integrate another complex control circuit to balance the voltage across this capacitor, then there is no use of this circuit. But as I have explained you here now, just now, this capacitor is getting charged in one level and discharging in one level. It means what? It is charging in parallel and discharging in series, right? So because of this charging, discharging and series in parallel, in one full cycle itself, the capacitor voltage will always be maintained at the desired voltage, that is the input voltage. So the another interesting thing is that you can avoid the auxiliary controller, or control complexity is not there at all. You can avoid the sensors, what is required generally in the real-time system to balance the voltage across this capacitor, that also can be avoided. So with respect to everything, this switched capacitor circuit is more advantageous than other circuits, and you can easily integrate photovoltaic system to this type of systems, right? So that we can get the boosting. You can also get self-balancing, what I call self-balancing. The capacitors are self-balanced, or you can say inherently balanced without any auxiliary controller. You can you are able to get the same multiple output or multi-level output at the load side or at the grid side, you can say. So with this, I'll stop the presentation here. Next time we'll continue with the demonstration of the switched capacitor of the same module. How you can do it in the Arduino based controller, we'll discuss regarding that. Thank you.
Yes, yes, Mr. Kaibalya, it's fine. The presentation part is very good. And can you take the question what the participant has given?
Yes, sure, sir. So that's Suvasish sir, I think he was asking a question I have seen in the chat box.
Yes.
If we are increasing the modulation index, that time switching angle will increase. No, you are actually, I think, wrongly interpreted. If you increase the modulation index, it is not that switching angle is going to increase or decrease. It is not like that. Switching angle will vary, but number of switching angle will not definitely not increase or decrease. Obviously, switching time will increase, you can say, right? Then what will be the firing sequence on K? Obviously, if you vary the modulation index, accordingly the switching angles will change. And as switching angles are changing, that is why, if you, I'll just go back to the previous slide, you can see here, when I'm changing the modulation index, why it is generating a 9 level output in the initial case, and why in the next case it is generating a 15 level output. That is because of the change of switching times. The switching instances are getting changed or varying. That is why the number of steps at the output is also getting changed.
And switching times and switching angles are different or what?
Yeah, no, same thing, sir. Switching angle is getting changed. But
That means
number of,
his question is relevant, I think.
no, the number of switching angles is not getting in the, what I want to say. The number of angles. Anything else you can, the participant can clarify me.
Sir, means I mean to say, if 15 level, in case of 15 level, so one-sided we are reducing the hardware. In case of 15 level, it will increase the hardware. Means hardware switching is increasing in 15 level. That time it will increase the switch number of switches. I meant to say number of switches that time. And angle also, if you are increasing, so that firing sequence, what will be the state of firing sequence? How will that logic sequence, how will maintain that time?
See, logic, this PWM logic is not going to change at all. This PWM
At all.
logic is set in the inverter, that is set. And this, because of the change in reference signal here, the reference voltage is there, that because of change in reference signal, the modulation index is getting changed. If modulation index is changing, accordingly, some of the switches are not getting pulse, right? The pulse is going to change because of the change in reference signal. So if the pulse is going to change, accordingly, the inverter will produce the output. Is that clear? So
yes.
What you are talking about, number of switch has been increased in the 15 level switch also. That is not if you compare with the conventional circuit. That is why I have also shown here some of the conventional circuits. With respect to conventional circuit, the number of switch is drastically reduced. If you see, you just consider a 15 level circuit in conventionally cascaded H-bridge type. So you require almost 28 number of switches. But here the circuit what I have shown only contains 10 switches. So you think of developing this circuit in the high power level. In that case, obviously your cost and size, volume, everything will be reduced drastically.
Yes, that angle is cosine of angle of that theta. If we are
Yeah.
increasing, if we are taking the theta, means number of harmonics, that cos theta 1, cos 5 theta, 3 theta,
Okay. Yeah. Yeah.
that
Yeah. Yeah.
even odd numbers of 5
Yes. Yes.
theta, 11 up to 11 and 13, up to
Yeah.
that time, how will be the sequence of that firing angle?
Very
That
good
I am
question
asking.
you have asked. Very good question you have asked. That is related to selective harmonic elimination control. If you are
Yes, sir.
thinking about harmonic elimination control only, then you need
Only.
to focus on cos theta 1, theta 2, theta 3, like that, how many angles and all. But here,
Yes.
as I have shown you, this is a phase disposition pendulum control scheme that is not related to selective harmonic elimination control here. So this is,
That uh,
yeah.
uh, that
So this is
modulation,
not,
if modulation index varies, that theta also varies that time, no?
yes, yes, definitely theta will vary. Yes, sir. Yes,
Theta varies.
yes,
Okay,
yes.
sir. Okay, I'm getting, sir.
Yeah,
Yeah.
thank you.